Hi, my name is Rajrishi Hazarika and I'm going to talk about the complexometric titration. It is the volumetric analysis in which the formation of a colored complex is used to indicate the endpoint of a titration. Let's see what is complexometric titration and its principle. A titration based on the formation of a coordination complex is known as complexometric titration, and it is basically used for the determination of metal ions and its principle. And let us consider one example to explain the principle of complexometric titration. Let us take a metal sample where calcium 2 plus or magnesium 2 plus ions are present. Then we add an indicator where we can use iridium black tea, and this will shows a color of wine red. Then we add EDTA from the burette. You can see this from the figure. EDTA, ethylene diamine tetraacetate. After addition of this complexing agent, this will form a new complex with calcium and magnesium ions, and the indicator iridium black tea comes out and becomes free. This EDTA complex is colorless and the color of this indicator is blue. As both are present in the same solution, the overall color of this solution becomes blue, and which is the endpoint of this titration. And this is the basic principle of this complexometric titration. Let's see the indicators used in the complexometric titration. Those indicators are also known as metal ion indicator. There are three main indicators used in complexometric titration. Those are iridium black tea, calmagite, and murexite. Iridium black tea is used to determine calcium, magnesium, barium, zinc, cadmium, lead, and mercury metal ions. Then the second one, calmagite, is used to determine calcium, magnesium, and cadmium ions. And the third one, murexite, is used to determine calcium, copper, and cobalt metal ion, etc. Now let's see the structure of iridium black tea. You can see this in the figure. And it is in the form of H2 ion negative. These two hydrogens come from this two OH group. It is in the acidic solution. In the neutral solution, it is in the form of H ion 2 negative and ion 3 negative in the basic solution. It is initially wine red in color, then it will convert it into blue, and finally it goes to orange. And that's how the iridium black tea indicator work. And this is the structure of calmagite. It is in the form of H2 ion negative. These two hydrogen comes from these two OH groups, and the negative signs come from this O negative. H2 ion negative, this is in the acidic solution. In the neutral solution, it is H ion 2 negative, and the basic solution, it is ion 3 negative. The starting color of this indicator is red, then it converted into blue, and finally goes to orange, same as the iridium black tea indicator. And the third one is murexite. The structure of this murexite is like this. It is in the form of H4 ion negative. These four hydrogens are 1, 2, 3, 4. These are hydrogens, and the negative signs come from this O negative. And in the neutral solution, it loses one hydrogen and become in the form of H3 ion 2 negative, and in the basic solution, it is in the form of H2 ion 3 negative. Starting color of this indicator is red violet. That in the neutral solution it becomes violet, and in the basic solution it is in the color of blue. Let's see what is masking and demasking agents. Masking agent, it is used to mask the impurities present in the analyzed solution. For example, if you want to analyze the calcium ion in any solution, and in the same solution magnesium ions are also present, then in that case magnesium ions are required to mask. Otherwise we will not able to get the exact concentration of calcium ions. There are two methods of masking impurities: precipitation and complexation. In the precipitation, we use sulfide, sulfate, oxalate, and thioglycerol. Sulfide is used to precipitate lead and copper. Sulfate is used to precipitate lead and barium, and oxalate is used to precipitate calcium and lead, and then thioglycerol is to precipitate copper ion. And the second method is complexation method. This method is more useful than the precipitation because here more stable complex is formed. And in the precipitation method, there may be a chances of co-precipitation occur. In the complexation method, we use ascorbic acid to mask the iron metal ion, potassium iodide to mask mercury, potassium cyanide is used to mask silver, copper and mercury, and then ammonium fluoride is used to mask aluminum, iron, metal ion, etc. Let's see how the masking agents works. It is a technique of releasing the masked species so that it is free to react with the principal reagent, and the masking agents are used to counteract the effect of a masking agent. And using this technique, we can calculate the individual concentration of each metal ions present in an analyte solution. To explain this, let us consider another example. Here we take a analyte solution where calcium, cadmium, copper, these three metal ions are present. And in step 1, we directly titrate with EDTA. Here, this calcium, cadmium, copper ions forms complex with EDTA. From this, we can get the combined concentration of calcium, cadmium and copper ions. In the second step, we use a masking agent. Here we use potassium cyanide and it will mask the cadmium and copper ion. Then again, if we titrate it with EDTA, and only calcium ions forms complex with EDTA. These two cadmium and copper ions are masked. From here we can get the concentration of calcium ion. And in the third step, we use a demasking agent. We can use chloral hydrate or formaldehyde, which will release the cadmium ion. And again, if we titrate with EDTA, calcium and cadmium ion forms complex with EDTA, but copper is unable to form complex with EDTA. From this, we can get the individual, after calculation, we can able to get the concentration of each metal ions. You can see this X from the step 1, we can get the combined concentration of calcium, cadmium and copper. From the step 2, we can able to get the concentration of calcium, and in the step 3, which is if we take as Z equal to combined concentration of calcium and cadmium. After this, we can, if we calculate, then we can able to find the concentration of calcium, which is Y, cadmium Z minus Y, and copper, concentration of copper is X minus Z. And that's how we can able to find the individual concentration of each these three metal ions present in the analyte solution, which is the benefit of using a demasking agent.